Welcome to this next lecture on acoustics. We had just started deriving the acoustic wave equation, and we were justifying the assumptions that were going to come. Let me also mention here that the boundary layer that comes up in acoustic wave propagation in air, the boundary layer thickness is a fraction of a millimeter. So they are a fraction of a millimeter. And that's where the main losses occur. So if one has to account for losses, it has to be accounted there. Okay. So now let's begin. So we start with the continuity equation. Which is del rho by del t plus del dot rho u is equal to q. Okay. So what are these? The rho is rho of x comma y comma z comma t. Okay. This is the total density at a point, total density at a point, and the capital U x comma y comma z comma t is the velocity vector at a point, the fluid, point in the fluid. Then q of x comma y comma z comma t is the mass source term, okay, just kg per meter cube second. Okay. So I'll number this. So let's say numbering, this is 1, this is 2, and that is 3 already. Okay. So 1 is temporal density change, rate of change. Okay. Rate of change of density. Then number 2 is the net mass outflow, from a point. Okay. Then the third term is mass entering. Okay. From a source. So each of these terms, okay, all the terms in this equation have m over length cube into time units. It's important. Okay. So that's first stage. So essentially what this is saying is that the change in density at a point plus the net mass outflow must equal the mass added from the sources, added or subtracted from sources. Okay, that's your continuity. The next is momentum balance. Okay, the Navier-Stokes equations. We will use the Stokesian approximation or assumption and take a form of this equation, which is rho del u by del t plus u dot del u is equal to the negative gradient of pressure plus a mu del square u plus 1/3 del of del dot u plus a rho times f bar. We will number these equations 1, 2, 3, whole thing will be 4 and 5. Okay, so here p x comma y comma z comma t is the total pressure at a point. Then mu is equal to the coefficient of viscosity, then f bar is the body force term, body force vector, okay, and just say that LHS represents the inertial terms, and RHS the external factors, external forces. Okay, now term 1 of course is the unsteady term, unsteady local acceleration. Okay, 2 is the convective acceleration term, 3 is the hydrodynamic forces, that come up due to pressure variations, The number 4 are the viscous forces, okay, or the viscous term, let's call it the viscosity term. Okay, so that is the cause of dissipation, and we have discussed how we are going to deal with it. Okay, then number 5, the body force term, body force term, that represents say gravity or other electromagnetic forces, if the fluid can support it. Okay, or electrostatic forces, and so forth. And all these terms, all the terms have units of m over L square T square. Okay. Now, as in the list, there are two more equations. I am not numbering or not numbering. Okay. So, the next is the equation of state for an ideal gas, which I will write as PV is equal to mRT. Okay. And then of course equation for energy conservation, which is first law, conservation, first law of thermodynamics, and I will use this form T ds is equal to du plus P dV. Okay. So, now let us first work on the Navier-Stokes equations. Navier-Stokes. Okay. So, as we said, we are going to ignore viscosity, neglect viscosity. Okay. Then next we are going to say that the okay, let's do this. So, let's do this. If we neglect viscosity, what do we end up with? Okay. Okay. Okay, and we neglect the convective term. Neglect the convective term. Okay, why we do that? Okay. So, what I am going to say here is that a special gradient or gradient introduces a length scale L okay. So, if I have some del of something or del x of something, okay. So, this is going to introduce a length in the denominator. Okay. Why do we say that? Let me just, so suppose my pressure or some quantity is some constant e to the power of minus jkx and e to the power j omega t. So, if I take a gradient or a special derivative, I will end up with a minus jk in the front. K is 1 over lambda. K is proportional to 1 over lambda. Okay. So, a special derivative brings about a length scale in the denominator. Okay. And a temporal derivative, what it does, temporal derivative del p by del t brings about a j omega, which is j over the time period t. Okay. So, it brings about a time scale in the denominator. So, time scale in the denominator. Okay. This length scale is a wavelength at a certain frequency, this time scale is the time period of that frequency, because we will be dealing with harmonic waves, that is important, harmonic. Okay. We will be dealing in this entire acoustics with this sort of waves. Okay. So, gradient introduces a length scale in the denominator. Okay, we have this term now here. Okay. So let us see, we will look at terms 1, 2 and 4, 1, 2 and 4. Okay. And we have said that a temporal derivative brings about a time scale and a spatial gradient brings about a length scale. Okay. So what we have over here is the left side. Okay. Now let me just take it separately, rho del u by del t plus u dot del u, I will write as rho u bar by t plus u bar square over L. Okay, there is only one gradient. Okay, that is this term on the left, 1 and 2. Okay. Now the term 4 happens to be mu, okay, and del square gives me u bar by L square plus 1/3. I have a del of a del dot u, so again I get u over L square. Okay. So that gives me a 4/3 mu u bar by L square. Okay. So we have these two terms. I have this term and I have this term. So let us multiply both of them by time. So I multiply this by a time scale t and the time scale t. So then what happens, I have this term ends up as rho u bar plus rho u bar squared into t by L or L by t in the denominator. Okay. This L by t I am going to take as the speed of sound. Speed of sound. Okay. So this term looks like rho u bar by the speed of sound, and this term looks like 4/3 mu u bar by L by C. Okay. So I have rho u bar, I have rho u bar into u bar by C, and I have 4/3 mu by L u bar by C. Okay. So now I am going to drop those terms that contain u bar by C in comparison to the others. Okay. So this has rho u bar and this has rho u bar and this term, so I am going to drop this. Okay. Similarly, I am going to drop a term which has u bar by C in it, because we have said in the beginning that it is much smaller than 1. Okay. So we are going to drop this. So out of 1, 2 and 4, 1 is going to survive. Okay. So the equation now looks like rho del u bar by del t is equal to minus del p plus rho f bar. Okay. Now I have not numbered these equations, so in some manner let me call this a 4. Okay, let me call this number a 4. Okay, so what will we do? So we'll call this together as 3. Together we'll call this as 3, and then I have this as 1 and this as 2. Okay, I will need it later. Okay, so this is one stage I have, the stage I have reached. Now what is the next? Okay, we have the continuity given by del rho del t plus del t, I mean okay, hold on. Plus del dot of rho u is equal to q. That was the equation. Okay, so now this was the continuity equation. So we will take a derivative, we will take a temporal derivative, time derivative. So this becomes del 2 rho by del t square plus del by del t of del dot rho u is equal to del q by del t. Okay, and this was numbered as okay, so we will renumber this as 1. Okay, and we take the spatial derivative or gradient or the divergence of this. Okay, so we do del dot of rho del u by del t is equal to minus del square of p plus del dot of rho f. Okay, we will call this 2. We are renumbering. Okay. Now for the moment, I don't know if I am listing also. Okay, so we're going to list this as assumptions. 1, 2 assumptions. So the third and fourth. Third assumptions, no body forces. Fourth assumption, no mass sources. No mass sources for the moment. Okay, sources. Okay. Now so the term 1 in equation 5, okay, term 1 in equation 5, let us see here. Already this term has volume velocity, mass flow velocity, mass flow rate, mass rate per unit volume. Okay, per unit volume. So now here this has become the rate of change of that. This has become the further derivative of that. Okay. So So that is how this term will enter. Okay. The mass rate, Q already has mass rate, and now you have a further derivative of that. So the rate of change of the mass rate is going to be entering the acoustic wave equation. That means a uniform velocity Q is not going to give you sound. Okay. If there is a source that is blowing a uniform air, it is not going to create sound. You need a rate of change of that. Okay. So this now has a second square in the denominator. Rate of change of that is what is needed to generate sound. Okay. Now this term, this number 1 term, is typically used to model a speaker. Okay. So which we will call a monopole. We will call a monopole if its dimension becomes small, if dimension is small. Okay. Now what sort of a source is it? It's a localized region where it is putting out a mass of air and it's pulling in a mass of air, sucking back the mass of air. Okay. So on an average, if you integrate around the source, it is going to have a certain non-zero value of volume or mass. Now the term 2 is like a piston with no baffle. Piston with no baffle. No baffle. What do I mean by that? It's like this source, a flat source, let's say, in the middle of the medium, and it is oscillating back and forth. It's oscillating back and forth. So this is like a dipole. That means when it's moving to the right, there is negative pressure here, there is positive pressure here. When it's moving to the left, there is negative pressure on the right, positive pressure. Okay. So now this sort of a source is called a dipole like source, because if you integrate around this source on a net basis, the volume velocity or mass flow is 0. Volume velocity or mass flow is 0. So when the source moves towards the right, as it compresses the medium on the right, the fluid escapes to the backside. Okay. The fluid has a chance to escape to the backside, whereas it is not so over here. Okay. So this is a different type of a source. It's a monopole type source, and this is a dipole type source. And because this fluid has a chance to escape, it is less efficient. It is a less efficient source, and it is represented by this divergence term. Okay. So now if we have numbered our equations, this is going to be called number 5, this is going to be number 6. Okay. So after these further assumptions, we will write 5 and 6. What do? We write 5 and 6 as del 2 rho by del t square plus del by del t of del dot rho u is equal to 0. I'll number it as 7, and then del dotted with rho del u by del t. Okay, that is going to be equal to minus del square of p, that I will call it as 8. Okay. So, we have run out of time. I will stop here and we will continue from here in the next class. Thank you.